It's been another year of observations with the James Webb Space Telescope. And now this telescope is fully operational and we are seeing science discoveries come faster than ever before. Now at Universe Today, we have been reporting on hundreds of stories from the James Webb Space Telescope over the last year. And we just want to share a fraction of some of the stories that we've been covering, some of the best pictures, the coolest nebulae, the most interesting discoveries, the findings from astronomers that take us back to the very beginning of the universe and teach us an incredible amount about this cosmos that we live in. Now, before we get started, I want to give you some perspective, and that is that I have organized all of the findings for this year's discoveries in terms of distance. And so we're going to start very close to Earth here in the solar system. Then we're going to move into the realm of exoplanets. Most of these exoplanets are relatively close to us here on Earth, cosmically speaking. Then we're going to shift to objects and discoveries that have been made by James Webb within the Milky Way galaxy. And then we're going to go cosmological. We're going to go outside the galaxy, looking at other galaxies, to quasars. And by the end, we are going to reach the very edge of the observable universe as seen by James Webb. So let's begin our tour through year 2 with the James Webb Space Telescope. Jupiter's moons. So let's start with the solar system. Unfortunately, we actually don't have a lot of amazing images of the solar system shared by James Webb this year. We got a lot of great images last year with the first ever images taken by James Webb of Jupiter, of Uranus, of Neptune, of Mars. But this year there's been a lot of data, a lot of interesting discoveries. So I tried to kind of boil this down. So first up, let's look at the moons of Jupiter. And right now you're looking at an image of Jupiter's moon, Ganymede. Ganymede is the largest moon in the solar system. And like Europa, it has this thick shell of ice surrounding what is probably a water ocean. And there might be geysers venting material from inside Ganymede out into space. But scientists have a lot of questions about the surface composition of Ganymede compared to other objects in the solar system. And so they pointed James Webb at Ganymede and they were looking for hydrogen peroxide, which is blasting off of the surface of Ganymede. This is caused by charged particles, some which are trapped by Jupiter's magnetosphere, as well as charged particles coming from the sun's solar wind that are slamming into the surface of Ganymede. They are breaking apart molecules on the surface, and they're creating clouds of hydrogen peroxide. And so astronomers were able to map the concentrations of hydrogen peroxide around Ganymede to measure the amount of interaction between Ganymede and these various charged particles in its environment. Then they shifted James Webb to look at Io, which is the most volcanic moon in the solar system. And with Io, they were able to measure concentrations of sulfur oxide coming from specific volcanoes on the surface of Io. And so when you match this up with images of Io taken by, say, the Juno spacecraft, you can get a much better sense of how Io is interacting with its environment. And then Webb looked at Europa, which is one of the most fascinating objects here in the solar system. Again, large, icy moon with an icy shell covering a liquid water ocean. And one of the big questions that astronomers have is, what kind of interaction is that ocean having with the icy shell, as well as how much of that is being vented off into space? And so Webb was able to find concentrations of carbon dioxide in specific regions of Europa. And carbon dioxide is a chemical that you should not see on the surface of an icy world. There's no atmosphere, it should be blowing away. And so there has to be some kind of source that is replenishing this carbon dioxide on the surface of Europa. Now, could it be European space whales blasting their carbon dioxide into space? Probably not, but it might be another hint that there are geysers on Europa. Unfortunately, Webb didn't detect any geyser plumes. Uranus's faintest ring. Let's move farther out into the solar system to Uranus. And in the first year, we got an image of Uranus taken by Webb. And in fact, we did voting on our channel, and many considered to be their favorite image taken by Webb of the entire year. And so we got a new, even better image of Uranus. And I think the best image of a planet taken by Webb in year 2. You're looking at the planet has been tilted over completely onto its side. And so we're looking down one of its poles and you can see the rings of Uranus face on. What's different about this year's Uranus image is that you can see the much fainter diffuse Z ring, which wasn't visible in the other image. And actually taking images of Uranus is quite complicated because the planet is spinning so quickly. It only takes 17 hours to complete one rotation. And so astronomers weren't entirely sure that Webb would be capable of taking images of fast-moving objects here in the solar system. But we've learned after these first 2 years of operations that yes, indeed, Webb can take images of fast rotating objects like Mars, like Jupiter, like Saturn, and Uranus. And that's it for the images that I want to share here in the solar system. And like I said, there was a lot of other interesting scientific discoveries that were made with Webb in the solar system, such as observations of Kuiper Belt objects and asteroids and active asteroids. There's a lot of great images, but we just had to shortlist down to what I thought were the best pictures taken this year. Now let's move to the realm of exoplanets. This is one of the primary science objectives of James Webb, is to teach us more about the atmospheres of exoplanets. And in general, what Webb is doing is it's watching as a planet is passing in front of its star. This is known as a transit. By focusing just on the light that's coming from the atmosphere of the planet, Webb can help astronomers determine what that atmosphere is made of, detect the presence of weather. There's a lot of really amazing discoveries. And so while we don't have a lot to talk about in the solar system, we have so much to talk about with exoplanets. Looking at the TRAPPIST-1 system. The closest planetary system that we're going to talk about in this video today is the TRAPPIST-1 system. And this is one of the most famous exoplanetary systems as well. You've got 7 Earth-sized worlds. At least 4 of these planets are in the habitable zone, which means that liquid water might be present on the surface of these worlds. One of the most anticipated discoveries this year is, are there atmospheres on the planets orbiting around TRAPPIST-1? And the answer is, we don't know yet. But we do know that there are no atmospheres around the first 2 planets. The anticipation was that TRAPPIST-1b and TRAPPIST-1c would have some kind of thick carbon dioxide atmosphere, kind of like Venus in our solar system. But Webb was able to make very detailed analysis of both these 2 inner planets, and it didn't find any hint of an atmosphere at all. And so you don't have Venus analogs. Imagine super Mercuries, airless worlds, kind of like the moon or Mercury that are orbiting around the star. And this isn't that surprising. The intense radiation that's coming from the star, the solar flares, are thought to scour these planets of their atmospheres. And so all hope is resting on the other planets. And here's where I've got bad news. And that is that we don't know the answer yet. In theory, Webb has taken the data, searching for an atmosphere for TRAPPIST-1d and the rest of the planets in the system. And yet, we haven't heard any announcement from any scientists that are working on this that they have discovered an atmosphere or that they have ruled out an atmosphere. So right now, the results are inconclusive. And so we're going to probably have to wait till sometime next year to find out whether or not they found an atmosphere. But the scientific consensus seems to be that these planets orbiting around red dwarf stars are likely to be blown away by the intense solar flares that these red dwarf stars can experience. And although they're hoping, because these are the kinds of planets that James Webb can observe, it could very well be that they just don't have any atmospheres at all. And we're going to have to wait for a much more powerful telescope like the Habitable Worlds Observatory to be able to actually image Earth-like worlds orbiting around sun-like stars and measure their atmospheres. I know many of you were hoping to hear some solid answer about whether or not there's an atmosphere around the TRAPPIST planets. And so far, we don't know the answer yet. An exomoon around a brown dwarf. Let's move a little farther out now to a brown dwarf. One of the big questions that astronomers have right now is whether or not there are moons orbiting around exoplanets. Like, obviously they're out there. I mean, we see how many moons there are here in the solar system, but nobody has actually found an exomoon orbiting around an exoplanet. This year, David Kipping and his team is going to be attempting to make a discovery of an exomoon, and so we can wait on that, but that maybe will show up in the year 3 version of this video. But we did get the hint of an exomoon orbiting around a brown dwarf. So James Webb was observing a brown dwarf, and this is a failed star, a star that has just not enough mass to be able to have hydrogen fusion in its core. And the star is very cool. It's merely 200 degrees Celsius. But one surprising discovery was that James Webb detected the presence of methane in the atmosphere of the star. And that's a very surprising discovery because normally you shouldn't see methane in the atmosphere of a brown dwarf. And in order to get this methane in the atmosphere, astronomers think there's some kind of temperature inversion. Something is heating up the exterior of this brown dwarf so that you're seeing the presence of the methane in the upper atmosphere. What's also interesting is the brown dwarf has auroras. When you think about auroras on Earth, we've got the solar wind coming from the sun, you have the Earth's magnetosphere that is channeling those particles, and you're getting this ionized particles in our atmosphere, and you get this green glow, the auroras. But there is no partner star that is sending a solar wind that's hitting this brown dwarf. So it has to be generating the aurora internally. But the intriguing theory is that if there is a moon, then it can be passing through the magnetosphere of the brown dwarf, generating this aurora. And so this could be the first indirect evidence of a moon, a satellite orbiting around a brown dwarf, thanks to James Webb. Asteroid collisions in another star system. Now I'm going to talk about something that James Webb didn't see that is actually incredibly scientifically fascinating. So several decades ago, astronomers were looking at a newly forming star system called Beta Pictoris. It's about 63 light years away. And they used the Spitzer Space Telescope to observe the system, and they detected large clouds of dust. They thought there could be a couple of reasons why there would be all this dust in the Beta Pictoris system. One idea is that you've got asteroids crashing into each other that are forming a bunch of dust. And this is like a one-time event. And then if you then looked at Beta Pictoris another time, maybe you wouldn't see all this dust. It meant it was a very temporary thing. The other possibility is that there's these just small particles of dirt that are grinding against each other, and they're creating all of this dust in the system. And so now, decades after Spitzer made its first analysis of the Beta Pictoris system, astronomers used James Webb to do follow-on observations, and it didn't see the same dust. And so that gives evidence of the asteroid collision, that when Spitzer happened to be looking at the Beta Pictoris system, it was actually seeing asteroids that had crashed into each other. The first Hycean world, maybe. When we think about planets, we say that they have to be in the habitable zone, this place where liquid water can exist on the surface of an exoplanet. But in the last couple of years, there's an entirely new kind of planet that's been proposed. This is known as a Hycean world, a planet with a thick hydrogen atmosphere surrounding a liquid water surface. So it's a portmanteau: hydrogen, ocean, Hycean. By having this thick hydrogen atmosphere, it acts like an insulator that allows you to have liquid water on the surface of the world. And so with this combination, the traditional idea of the habitable zone goes out the window. You could have this world be a lot closer or a lot farther from the star, and yet it could still have liquid water on the surface. And the best candidate that astronomers have found so far is known as K2-18b. It's located about 120 light years from Earth. The planet is big. It's about 3 times the size of the Earth. And thanks to James Webb, astronomers were able to detect the presence of both methane and carbon dioxide in the atmosphere. And this gave them an indication that this is one of these Hycean worlds. But there was another chemical that astronomers said they got a faint whiff of, which is called dimethyl sulfide, or DMS. On Earth, this chemical is almost entirely produced by phytoplankton, by life. And so you could imagine there's this water world that's surrounded by this thick hydrogen atmosphere. There's giant blooms of phytoplankton floating around in the seas. They're producing this dimethyl sulfide, and we get this measurement. So life found, right? Well, not so fast. So according to other astronomers, to be able to get that clear of a signal of dimethyl sulfide in the atmosphere of K2-18b, then it would have to be producing about 20 times the concentration of this chemical than what we see here on Earth. The problem is that the signal for methane and the signal for dimethyl sulfide overlap. And so although it's possible that they detected DMS, it's also possible that the signal from the methane is overwhelming it and causing an error in their observations. But there are other explanations for this planet that have nothing to do with water and nothing to do with life. So another team of astronomers looked at the data coming from K2-18b, and based on their calculations, the best explanation would be a world that is covered in lava. And the key to this is that they were looking for another chemical in the atmosphere, which is ammonia. So in other words, in addition to the methane and the dimethyl sulfide, they were hoping to see ammonia. They didn't see any signal of ammonia in K2-18b. And so instead of it being this water world covered by life, it could just be a rock world covered by lava. And then another team looked at the data and they said, actually, you could get all of this with a gas-rich mini Neptune. It's not the kind of planet that we have here in the solar system, but imagine Neptune, but smaller. It could also provide the same kinds of gases in its atmosphere to explain those observations. So the point is, like, don't be too excited that people have found life. I know there was a ton of stories out there this year. The K2-18b, this is it, life found. You should be more skeptical, reserve your judgment, wait for the data to come in. There are plenty of explanations, and you can see astronomers are still arguing over what it is that they found. They're not sure about the life, and they're not even sure what kind of planet it is. So stay tuned. Methane in an exoplanet atmosphere. Let's move farther out into the galaxy to a planet called JWST. And this is a Jupiter-like planet, not a hot Jupiter, one of these ones that's orbiting really close to the star, but more like a warm Jupiter with a surface temperature of about 550 Celsius. And as I mentioned earlier, James Webb was able to watch as the planet passes in front of its star. It was able to measure the chemicals in the atmosphere of this planet. And one intriguing discovery was they detected the presence of methane, just like they had detected it with that brown dwarf that I mentioned earlier. Methane is incredibly exciting because it's a very short-lived chemical. And on Earth, the atmospheric methane is largely produced by life. You've got various forms of methane, rotting vegetation, you've got various bacteria that release methane, burping cows. Oh, people always just hate it when I say burping cows. They burp, they do. But there are inorganic ways to get methane as well, volcanoes. And in fact, think about worlds here in the solar system. Titan has lakes of liquid methane. It rains methane, and yet it was probably some kind of inorganic process that led to that methane. What's going to be more interesting is to see how the presence of methane in the atmosphere interacts with other chemicals like carbon dioxide, carbon monoxide, water vapor, and that it may be that in the future we could say, if we see methane and other chemicals and watch the interplay of those chemicals in the atmosphere, then that might give us some kind of indication whether or not there's life there. Weather patterns on an exoplanet. Webb is not just mapping the concentration of chemicals in the atmospheres of these exoplanets. It is also measuring the weather. So astronomers looked at a planet called WASP 43b. And this is a tidally locked planet. It orbits incredibly close to its star, about 1/25th the distance from Mercury to the sun. When a planet transits in front of a star, it actually makes 3 transits. You've got the transit where the planet is passing directly in front of the star, but you've actually got where the planet passes behind the star, and then when the planet reappears on the other side of the star. And if the planet is close enough to the star, you get several of these transits that you can watch every couple of days. And so astronomers were able to measure the difference in the chemical constituents between the day side and the night side because the planet is tidally locked to its star. And they found that it has cloud cover across the night side, the part that is facing away from the star, but clear skies on the side that is facing the star. It also has enormous equatorial winds that are blowing at about 8,000 kilometers per hour that is distributing material from the day side to the night side. And because most of the planets that James Webb is analyzing so far, these tidally locked planets, what weather is happening on a sort of more massive version has some implications for the kinds of smaller terrestrial planets that they're hoping to see around red dwarf stars, which are also going to be tidally locked. So although we don't know if there is atmospheres around the TRAPPIST-1 planets, we can get a sense of how they might behave. Water delivery to new planets. One of the long-standing questions in planetary science is, how did Earth get its water? Now, Earth is too close to the sun for water to remain on the surface of the planet without the atmosphere and the magnetosphere protecting us from the solar wind and the radiation coming from the sun. And so early on in the Earth's history, when it didn't have that protection, any water that would have been on the surface of the planet would have boiled away and gone off into space. So scientists believe that the water was delivered later. Well, where did this water come from? One possibility is that the water came from comets that came from the outer solar system. Maybe they came in from Kuiper Belt objects that were closer in, or maybe there was just icy particles close into the solar system that the Earth picked up and accumulated over time. Well, now Webb has watched this process in action around another star system. It was able to detect water-rich particles drifting from around Neptune distance towards the inner system. And so these observations by James Webb nicely match one of the leading theories about how planetary systems get their water. It's known as the icy pebble drift theory. Now we've just got this example of an exoplanetary system with water being delivered into the inner solar system. A planet with clouds made of sand. Another crazy exoplanet. This one is known as WASP 17b, and it's much farther away than any other exoplanets we've been talking about so far. And it's considered a puffy Jupiter, which is that it has a large outer atmosphere that's heated up to about 1500 Celsius. It's almost double the size of Jupiter, but only about 78% of its mass. And so it has a very low density and it's like puffed out significantly. Because the atmosphere of this exoplanet is so hot, astronomers wanted to know what kinds of chemical processes could happen that are different from cooler worlds like Jupiter and Saturn here in the solar system. And they found aerosols in the atmosphere of this exoplanet. And this is the kind of thing that we have here on Earth, but unlike Earth, the aerosols are made of quartz, of sand. There are clouds of sand in WASP 17b. And this is puzzling because in order to get sand, you need to get the crystallization of silicon oxide. You need to have molten liquid silicon oxide, and then it needs to be able to cool down and crystallize to form quartz. But the temperatures are so incredibly hot. And so WASP 17b instead has been able to, under high pressure and high temperature, force the silicon oxide into its crystals to form the sand that makes up its clouds. What a crazy world. Rogue planets in the Orion Nebula. I'm going to put this on the short list of the most profound discoveries made by James Webb in year 2. And this is the observation of hundreds of rogue planets in the Orion Nebula. Also known as free-floating planets, these were actually first discovered by the Hubble Space Telescope several decades ago, but they only knew of a handful of them. And so they knew James Webb, with its infrared capabilities, would be able to see many more of these objects because they're cooler, they glow in the infrared. So as I mentioned before, Webb was able to find 540 of these objects free-floating in the Orion Nebula, some of which are even smaller than Saturn. And they also found 42 of these objects that are in orbit around one another. So the new term for these objects is Jupiter Mass Binary Objects, or JUMBOs. And so now the big question you have is, how do these form? Imagine you've got just Jupiter free floating through space. Did it form in some existing planetary system and then through some kind of interaction it was thrown out into deep space? Or did it just form all on its own by a small amount of gas and dust? But if you got one that was just thrown out, then how do you have 42 of them that are in binary pairs? Did you get 2 thrown out at the same time? Did 2 separate individual rogue planets find one another and go into orbit? We have way more questions than we have answers, but we know that these things are very common. And I think what makes this discovery so profound is that it gives us a much better sense of what's actually in the Milky Way. That it's not that we see all of these stars and assume they're going to have all of these planetary systems around them, but in fact, there are billions of free-floating planets that are just drifting around inside the Milky Way. And I know you're going to ask, do those account for dark matter? And the answer is no. In addition to this amazing discovery, I think this picture of the Orion Nebula will look great on your computer or phone desktop background. This is your new wallpaper. A key molecule for life. So we talked about how Earth got its water, which is one of the important things for life on Earth. But the question is, how did Earth get its organic molecules, all of the various carbons and nitrogens and oxygens that were needed for life to form its various elements. One possibility is that all of these chemicals were delivered and then they started to form larger compounds here on Earth. But astronomers are finding more and more examples that these chemicals were already present out there in the universe in increasingly larger and more complex molecules. All of the amino acids that life uses have been found just out there floating in space. But now, thanks to James Webb, astronomers have found an even more basic building block of life. So the molecule is called methylcation, CH3+, and it was found in the Orion Nebula, so in the same place that it found all of these free-floating exoplanets. And it's been long theorized that this molecule is out there, but had never been observed before. It's been tricky to find because it chemically wants to bind with other atoms, like carbon. And it was also surprising that you would find this molecule in this region that has tremendous amounts of ultraviolet radiation. It was thought that these would break them apart, but in fact, it seems to be replenishing the reserves of this CH3+, which can then form into interesting organic molecule compounds. And so again, maybe we know the source of the water for Earth, and now it really seems like we're finding the source of the organic molecules that were delivered to Earth. I guess the molecules for life formed long before our planet itself formed. Protoplanetary disks in the Lobster Nebula. We're going to move even farther away now to a region of space called the Lobster Nebula. NGC 6537. This is a dense star-forming region that contains hundreds, thousands of newly forming stars. But because there's so much mass and material available, you're getting a lot of the larger kinds of stars, classified as OB stars. And astronomers wanted to see, do these much larger stars still have protoplanetary disks? Could you get planets around these hot stars? And so James Webb was able to analyze the regions around these big hot stars. And because they're all very young, it was able to find the signal of planetary disks around these stars. They were even able to detect the presence of water in the habitable zones. And so it shows you that even the largest, hottest stars probably have planets. They probably have planets in the habitable zone. Life could be everywhere. Next up, let's take a tour of the Milky Way galaxy and some of the amazing objects and images that James Webb has been able to see relatively close to us, cosmologically speaking. James Webb images a young star. So first, I want to share an image of a Herbig-Haro object known as HH221. And this is a brand new star in the Milky Way. It's located about 1,000 light years away from us, and it's only just a few tens of thousands of years old. It only contains about 8% of the mass of the sun, but it is consuming additional material, and by the time it's done, it should end up being about the same mass as our sun. And so people always ask me, what would it look like if a star just started to turn on? And this is what it looks like. You're seeing a star that is younger than humanity, and yet it is starting to heat up, accumulate material. It's drawing in additional gas and dust from its surrounding nebula and whipping up these intense magnetic fields that will eventually create powerful jets that blast out again. This is what it looks like at the very beginning. The Horsehead Nebula. This was one of the most anticipated images to be seen from James Webb. This is the ideal kind of target for James Webb, the Horsehead Nebula. This is an incredible star-forming region in the Orion Nebula. It's close to the Orion Belt, and one of the classic images taken by the Hubble Space Telescope was of the Horsehead Nebula. I'm sure some of you still have it as your desktop wallpaper. Well, now we've got the James Webb version of it, but it's very different. So we got 3 versions of this nebula taken by 3 different telescopes. The first version was taken by the European Space Agency's Euclid mission. And then we got an image from the Hubble Space Telescope that zooms in. And then we got an image from James Webb that zooms in even more. So you're just looking at this tiny little piece of the nebula in incredible detail. And you can see all of these knots of gas and dust swirling around the mane of the Horsehead. And you can see background galaxies behind the nebula if you look very carefully. So now you'll have to swap out your desktop wallpaper with the new version. Herbig-Haro 4647. So now let's look at another set of newly forming stars, and this is Herbig-Haro 46 and 47. In other words, it is two separate young stars that are orbiting around each other, and these will eventually become a binary pair of stars. They're a little bit older than that star that I showed you earlier, and they are embedded in a similar cloud of gas and dust, and they are drawing material in. But because the two stars are interacting with one another and interacting with the larger gas cloud, you've got these really strange outflows that are coming away from the two stars. What I love about this picture is you're looking at what is known as a Bok globule. And so in visible light astronomy, if you tried to look at this same object, it would just look like this black cloud because the amount of dust blocks the light from the stars. But with an infrared telescope like James Webb, we can peer through that obscuring gas and dust and actually be able to see the region around where the stars are accumulating material. And so same thing, they're going to gather up additional material, and eventually their powerful stellar winds will kick in, they'll blow away all of the additional material, and we'll have two stars orbiting around each other. But that's still millions of years from now. The Ring Nebula. All right, this is an object that is very special to me, and this is an example of a planetary nebula. When a star like our sun reaches the end of its life, it puffs out, becomes a red giant, and blows away its outer layers. And then it shrinks back down, and then puffs out again, and throws out another set of its outer layers. And eventually it runs out of material and just shrinks down and becomes a white dwarf. And every planetary nebula looks different, and astronomers aren't entirely sure why. Maybe it's because they have a binary companion, or maybe it's the kinds of planets that they had, or just how much material was in the star, but they all look different. And the Ring Nebula is one that you can see with a small telescope. I've seen it many times. Of course, under the incredible resolution of James Webb, parts of this nebula that were blurry blobs are now these intricate little swirls of gas and dust that we can see with incredible resolution. And at the very center, you can see the white dwarf. This was the star that puffed out all of this outer material and then shrunk down and is now just cooling down to the background temperature of the universe. The Pillars of Creation. It just gets better and better. And so now we've got the Pillars of Creation. But actually, Webb was able to capture images of the Pillars of Creation in the first year of its operations. And so this year, astronomers working with James Webb decided they're going to do one better, which is they're going to take the data taken by James Webb, as well as the data captured of the Pillars of Creation by the Hubble Space Telescope, and turn it into a three-dimensional visualization that you can actually fly around and see what they look like as if you could fly through space. What you're looking at is giant newly forming stars that are surrounded in these clouds of gas and dust. And then the combined radiation from all of the stars in the cluster are blasting with their combined radiation, and they are blowing this material away. It's thought that the pillars might have already collapsed. They've already been blown away by all of this radiation. We're just seeing the events as they happened in the past. If you have a 3D printer, you can download the 3D objects for the Pillars of Creation and you can print them off and I guess paint them. So it's very cool that you can get a sense of what these look like in 3 dimensions. The Crab Nebula. The hits just keep coming. So now we've got the Crab Nebula, and this is probably the most famous supernova remnant that we've ever seen. And so ancient astronomers, when they looked into the sky, saw this brand new bright star appear. And in fact, they could even see it during the day. It lasted for several weeks and they didn't know what it was that they were looking at. I'm sure they thought that it meant bad omens or good omens. And now, 1,000 years later, we see this expanding cloud of debris left over from when this supernova went off. Because James Webb sees in the infrared, it's able to see a lot more detail than we could see with the Hubble Space Telescope or what you could see with your own backyard telescope. Incredible, intricate details in the Crab Nebula. So this is your new computer wallpaper. You're getting to a lot of computers and a lot of wallpapers. Yeah, maybe some way to switch through them quickly. Cassiopea A, another incredible supernova remnant imaged by James Webb. This is a star that exploded about 10,000 years ago, and it was observed in 1667. And so in this object, you are seeing the expanding debris cloud that's about 10 light years across, with material flowing out into space at between 4,000 and 6,000 kilometers per second. The shock waves are heating up all of this gas to about 30 million Kelvin. And so while Webb looks in the infrared, it's able to see the parts of the nebula that are cooler, dustier, while other telescopes like the Chandra Space Telescope are able to see the hottest regions where X-rays are being blasted out into space. The heart of the Milky Way. For the last part of our tour through the galaxy, we're going to go to the region around the very center of the Milky Way. Now, you probably know that there's a supermassive black hole at the very heart called Sag A star. The image that you're looking at is about 300 light years away from that very center part of the Milky Way. What makes this strange is that new stars are forming just hundreds of light years away from the very center of the galaxy. Stars are packed incredibly densely together. In fact, in this image, there are 500,000 stars. They're all putting out intense radiation, and this radiation should be blowing away all of the star-forming material that could be used to accumulate new stars and planets. And yet, stars are forming. Thanks to the infrared view of James Webb, it's able to see through the gas and dust to be able to find the regions where these stars are forming and give astronomers some clues about why this is happening. But even though James Webb can see through the gas and dust to the heart of the Milky Way, this region is so densely packed that it's even opaque in infrared. Those are the darker regions in this image. I hope you enjoyed the tour through the galaxy. Now we're going to expand our vision out to the very edge of the cosmos. We're going to go beyond the Milky Way to the nearby galaxies, to galaxies that are billions of light years away, and eventually to the very first light that was seen by astronomers. Supernova 1987A. Although we've left the Milky Way, this supernova remnant is just in our backyard. It's located 168,000 light years from Earth in the Large Magellanic Cloud. And many of you remember this time when a supernova went off in the Large Magellanic Cloud, named 1987. And because we detected this supernova in the modern era, astronomers have been able to watch this expanding ring of material year after year as it gets bigger and bigger. And this year, we got the first images of supernova 1987A from James Webb. Until now, astronomers hadn't found the neutron star remnant left over from the detonation of this star. And the hope was that James Webb would finally be the telescope that would be able to do it. But even Webb wasn't able to pierce the gas and dust at the heart of supernova 1987A to find the object. But they were able to confirm its existence. They didn't see it directly. They detected the presence of ionized argon at the center of 1987A. And that is not something that you should see. And so what the astronomers think is happening is the neutron star is in this veil of gas and dust. It is blasting out radiation. The radiation is ionizing nearby argon that was created when the supernova went off. And so that is evidence that there is this bright hot object in the middle of this nebula. NGC 604 in the Triangulum galaxy. Now we go a little farther away to a galaxy known as Triangulum. Now it is a member of the local group. We've got the Milky Way, we've got Andromeda, we've got a bunch of dwarf galaxies, and we've got the Triangulum galaxy. And in the far, far future, all of those are going to be merging together into one giant elliptical galaxy. But for now, we can see it. You can even see the Triangulum galaxy with the unaided eye if you know where to look. And in Triangulum is one of the largest star-forming regions that we know of, known as NGC 604. And it is an absolute monster, bigger than anything we have nearby in the Milky Way. Just for comparison, the Orion Nebula is 12 light years across. So this is more than 100 times bigger than the Orion Nebula. And so because it is a much larger nebula with a lot more material, it has a lot more of the most extreme stars in the universe. There are at least 200 giant stars in this image, some of which are more than 100 times more massive than the sun. And there are red supergiants that are hundreds of times larger than the sun. Think of like Betelgeuse, but even bigger, and tons of them. And yet, this entire nebula, all of its stars are less than 3.5 million years old. And because it's so young, we can see all of these big stars. They're all going to start popping off as supernova in the next coming few million years, and they'll all be gone. And then the cluster will start to break up and the stars will be mixed in with the rest of the galaxy. And what I like about this image is that they used several instruments on board James Webb to look at it in different versions. This is your new wallpaper. Face-on spiral galaxies. Now let's move out from the local group to galaxies that are not gravitationally bound to us. And this is a survey that was done by James Webb called the Physics at High Angular Resolution in Nearby Galaxies, or FANGS. The purpose of this survey is to understand how galaxies evolve over time, how the pockets of star formation get turned into new stars, how they can interact with the rest of their environment. And so it's just a whole bunch of really amazing pictures of galaxies. 19 were shared in one block, and this is just a fraction of all the galaxies that have been studied with the FANGS program. If you look carefully, you can see the spiral arms of the galaxy, which are highlighted in red. These are regions where gas and dust is being turned into new stars. You can see that some of the galaxies have active centers where there's a supermassive black hole that is actively feeding on material and blasting radiation out into space. This is just a fraction of the star clusters that the FANGS program has identified. In fact, so far, they've found 100,000 star clusters located in the spiral arms of different galaxies. The Whirlpool galaxy. So this is another extremely famous galaxy, the Whirlpool galaxy. And most astrophotographers have taken a picture of this galaxy. You're very familiar with what it looks like, this incredible face-on galaxy. This is part of that FANGS program that I mentioned, but probably the nicest picture and the one that's most familiar. And you can really see the spiral arms of this galaxy in incredible detail. These knots of gas and dust where stars are forming around the galaxy. And then the warmer gas and dust that's down at the very center surrounding the supermassive black hole. Up until this point, I've been talking about objects in terms of light years away. Things are tens of light years away, hundreds of light years away, millions of light years away. But I need to change the way I talk about distances, because the objects that I'm going to talk about now are moving away from us faster and faster. And so it doesn't actually make sense to say that they are billions of light years away. Astronomers would talk about this in terms of redshift. They would only be concerned with how fast this object is moving away from us, but that doesn't really make sense to us either. So instead, I'm going to talk about how long the light has been traveling to reach us, whether the light has been taking 1 billion years to reach us, 10 billion years to reach us, or the very beginning of the universe, 13.8 billion years to get to our eyes. Multiple gravitational lenses. Now, we've been talking about how the Milky Way is part of the local group, but the local group is part of an even larger cluster called the Virgo supercluster, which is part of an even bigger object. So the largest galaxy group that astronomers have ever discovered is known as El Gordo, which is Spanish for the fat one. And it is a galaxy cluster that contains 3 quadrillion solar masses. That is a lot. And because of the incredible, intense density of material in this galaxy cluster, it acts like a gravitational lens, a natural telescope lens. And so you've got galaxies that are in the background behind El Gordo that are being focused by the gravity of this galaxy cluster so that we can see them when we wouldn't normally be able to see them. So this foreground galaxy, El Gordo, the light has been traveling for 6.8 billion years. But we are able to see the light from galaxies that are much farther away. So for example, there's one called the Fishhook, where the light is traveling for 10.6 billion years. And another one's called the Thin One, where the light has been traveling for 11 billion years. And in fact, due to this gravitational lensing, astronomers were even able to find an individual red dwarf star, which is like unheard of to be able to see a star this far away. The farthest known star. I talked about that individual red dwarf star that was seen by Webb thanks to the gravitational lens of El Gordo, but that is not the most distant individual star that has ever been seen. That record goes to a star known as Erindel, which is the Old English name for morning star. And it was originally discovered in 2022 by the Hubble Space Telescope. But because it's looking at an object that is so far away, this is the ideal target for James Webb. Would James Webb be able to see the same object seen by Hubble? And the answer is yes. Now, it wouldn't even be possible to see this star if it wasn't for this gravitational lensing. You're seeing the light magnified by about 4,000 times by this natural telescope lens, this galaxy cluster that is magnifying the light of this distant star. And so the light from the star has been traveling for 13 billion years. Not only was James Webb able to pick out the star, it was able to tell that it's probably a B-type star, something that is larger and hotter than the sun, and maybe that it even has a companion star. Now, the next step is to actually try and measure the chemical composition, do spectroscopic analysis of the star, and maybe get a sense of the chemicals. It would be really fascinating to see a star as it looked less than 800 million years after the beginning of the universe. The cosmic web. When we look out into the universe today, we see the cosmic web, the large-scale structure of the universe. The gravity of all of these galaxies and galaxy clusters is pulling themselves together into these larger and larger objects. This is opening up gaps in between them known as voids. You're getting these structures, walls and filaments, but instead of individual stars or gas and dust, they're galaxies and galaxy clusters aligned in these larger and larger groupings. And yet, as we look farther and farther into the universe, earlier and earlier into time, we can see that this cosmic web started to form really at the very beginning of the universe. And so a study from James Webb looked for any evidence of the cosmic web and found it less than 1 billion years after the beginning of the universe. Astronomers found a thin 3 million light year long thread of galaxies. It's anchored on one side by a quasar, and you've got other galaxies lining up, starting to pull together into this cosmic web just 830 million years after the Big Bang. The most distant active supermassive black hole. Astronomers believe that there is a supermassive black hole at the heart of nearly every galaxy. The Milky Way has one. Andromeda has one. Most of the time, this black hole is quiet. It's out of food. But every now and then, material is fed into the heart of the galaxy, and the black hole roars to life. Builds up this giant accretion disk around it, magnetic fields whip up, and you get jets of material that are blasting out of the center of the galaxy. When one of these objects is directed towards us, we know this as a quasar. But in fact, there's a whole range of active galaxies that you're seeing this quasar jet in different angles. They can be called active galaxies, they can be called Seyfert galaxies, they can be called blazars or quasars. And because quasars are so bright, they can outshine the rest of the entire galaxy. At the greatest distances, all we really see are quasars. And now astronomers think they've found the most distant quasar so far, although this is the kind of record that will almost surely be broken. They found this galaxy as part of a survey at a time when the universe was just 570 million years old. And the quasar contains 9 million times the mass of the sun. Just for comparison, that's about double the mass of the black hole, the heart of the Milky Way, but it's a quasar. And so we are seeing it at a time when the universe was only 570 million years old. But this is just one of the quasars that James Webb analyzed. It looked at many others, and you're really starting to see that while in a more modern galaxy, a supermassive black hole only contains about 1% of the mass of the galaxy, early on in the universe, these supermassive black holes were a larger ratio of the galaxy, more like 10%. And so why has this number changed over time? This is one of the mysteries that James Webb is trying to help astronomers solve. The most distant galaxy. So this is a record that will not last for long, and this is that James Webb has identified the most distant galaxy known to astronomy. And the galaxy is called JWST Z14-0. And the Z14, this is the redshift. This is the distance to the galaxy based on the speed that it is moving away from us. This galaxy was a candidate that was part of a larger survey of galaxies that James Webb had found, and astronomers figured that this was probably the farthest, fastest moving, oldest galaxy that they were seeing in the field of view. And so they did a very detailed spectroscopic analysis of this galaxy. They looked at it for 10 hours using James Webb's NIRCam. And from this, they were able to measure that redshift of 14. And that corresponds to 290 million years after the Big Bang. But I wouldn't be surprised when we do this video next year, we talk about year 3, that there will be a new record for the most distant galaxy in the universe. Dwarf galaxies illuminated the universe. The most distant thing that we can see in the universe is the cosmic microwave background radiation. This is a time about 380,000 years after the Big Bang when the universe had cooled down to the point that light could finally escape. And we see this in the microwave spectrum. But then there was this time after the cosmic microwave background radiation was released when the universe went dark. There was just no stars, no galaxies had formed yet. And then over time, the first clouds of gas turned into the first stars, but they were shrouded in more gas, and so they're hidden from our perspective. But then these stars turned on, they pumped out enormous amounts of radiation, the radiation cleared out this material, and we got the first stars and galaxies in the universe. But not just the first stars and galaxies, just the material in between the galaxies started to heat up and give off radiation. And this is known as the Epoch of Re-ionization. And astronomers have wondered what triggered this time in the early universe. Was it the first stars putting out radiation? Was it early quasars, massive galaxies? James Webb used gravitational lensing to see the combined light of dwarf galaxies early on in the universe and found that they were contributing to the radiation that led to the Epoch of Re-ionization. And so, although this is sort of right at the very end of the video, this is one of the greatest discoveries made by James Webb this year and so far in its life, and has gone a long way to solving one of the biggest mysteries that astronomers have been puzzling over. And so with this last discovery, Webb has brought us to the very edge of the observable universe, the farthest that can be seen, to see as the first events are happening in the universe. And so that's it for our highlights of year 2 with James Webb. But of course, year 3 is just beginning now, and astronomers have been working, putting in all of their proposals for the kinds of science that they want to do for the next year of operations with James Webb. And in fact, you can watch the process for yourself. There's a special website you can go to where you can see where the Hubble Space Telescope is pointing, where James Webb is pointing, what science they're doing right now today. And so you can watch year 3 unfold in real time. I hope you enjoyed this retrospective of year 2 of James Webb. Now, this is a really condensed version of all of the news that we cover every week here on the channel through our Space Bites, through our question show, through all of the interviews that we do with the scientists that are working on James Webb and everything across the universe. And so if you haven't already, subscribe to our channel. I'm going to talk about some of my reflections on the year, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Bill, David Giltonen, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Modso, Paul Rohrbach, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our supporters on Patreon. It was really hard to condense down all of the big stories that we had this year from James Webb. We are probably reporting on 10 stories a week at Universe Today. We're covering at least 1 to 2 stories on Space Bites every week here on the channel. There's been a lot of news, and it just feels like it's accelerating. We're getting all of the stuff that was observed last year but was announced this year. We're getting all the stuff that was observed that is now coming into the public domain that any astronomers can look through and make their own discoveries. We're seeing responses to discoveries that are made, and it is like not an understatement to say that it is having a profound effect on the nature of astronomy, our understanding of the cosmos, our understanding of extrasolar planets. And when you think about the fact that this telescope is going to be with us for at least a decade, maybe 2, there's going to be so much more science that's coming. If you missed our first year rundown of everything discovered by James Webb, we're going to put a link to it here. All right. I hope you enjoyed this special on James Webb, and we'll see you next time.